Hi, this is Mr. Erlin doing the algebra review. That's homework number 35 for geometry. I'm just going to walk us through this. So the first is number sense. We're beginning with a PEMDAS rules, which says we do the parentheses first. So in this case, we'd get 15 divided by 4 minus 1 is 3. 15 divided by 3 is 5. Again, number sense, what do I do first? Well, this is a perceived division problem, this over this whole chunk. I got to do this whole chunk first. So I have to combine this and this. Well, these are fractions. So I'll turn this into a fraction first. I'm going to make it an improper fraction. So negative 1 and 2 more thirds is the same as negative 5 thirds plus 1/5. But now I'm combining two fractions that have different denominators. I need to get them to be a common denominator. So this is negative 6 over the common denominator for 5 and 3 is 15. So I'll multiply this one by 5 over 5 and this one by 3 over 3, giving me negative 25/15 plus 3/15. So now I've got negative 6 over, these have a common denominator, so I can combine them to make negative 22/15. Now I'm taking a whole number divided by a fraction. Easiest way to do that is take that whole number times the reciprocal of that fraction. So 15 over negative 22. When I multiply a whole number times a fraction, I should turn that whole number into a fraction by putting it over 1. And what I get is negative 6 times 15, which is negative 90 over negative 22. And I can reduce this or cancel as appropriately. First of all, there's a negative on top and a negative on the bottom. Those cancel. I can divide 90 by 2, and I can divide 22 by 2, and I get 45 over 11 as my answer. And that's an improper fraction because the top is bigger than the bottom, and that's fine. You can leave it like that. Could I also see how many 11s go into this? There's 4 of them, and call it 4 and 1/11. Sure, that would be fine as well. PEMDAS, D-A-P-E-M-D-A-S. You know, the M comes before the D, but I don't do multiplication before division because they're both considered the same operation. Instead, I go left to right when it's all the same operation. So 6 divided by 3 is 2, times 4 is 8. All right, I'm going to do what's in the parentheses first. This is subtraction, this is multiplication, so I'll do multiplication first. These are both negative numbers. I'm taking a negative 14 and subtracting 6 more. That's going to make it an even lower number of negative 20. All right, evaluate. So now I'm plugging these numbers in. M is negative 3, so negative 3 minus whatever Q is, minus negative 3 plus whatever Q is, and Q is 5. So we'll do what's inside the parentheses, or the absolute value first. This is negative 3 minus 5 minus negative 3 plus 5 is 2. And the absolute value of 2 is still 2. In other words, the absolute value doesn't need to do anything unless this is a negative number. So negative 3 minus 5 minus 2. I can express this if I want as negative 3 plus a negative 5 plus a negative 2. In other words, I'm adding 3 numbers that are all negative together. Therefore, my answer is the sum of those values, all with a negative number. Next, I'll do the, again, evaluating. So I'm going to take Z of 7. 9 is for Y. So when I multiply this, I multiply it as a fraction, top times top, bottom times bottom. 7 times 9 is 63 over 3, plus regular 9, because the absolute value doesn't have to do anything. 63 divided by 3 is 21, plus 9, so my total is 30. Now we're going to be solving equations. When we solve equations, we're asking what's being done to the variable, and then we're undoing that. So I see that M is being divided by 13. I'm going to undo that by multiplying by 13. And if I do it to the right side of the equation, I need to do it to the left side of the equation as well. So 13 times negative 3 is negative 39. And this 13 and this 13 cancel. That was the reason I did it. This is the way I could leave it like this. I could also apply that symmetric property of equality that we've been dealing with and say that M is negative 39. Here, K is having 77 added to it. I need to do the opposite of that. So I'm going to subtract 77. If I do it to one side, I do it to the other side. So that leaves just a k on this side as I intended. And here it's 5 more into the 100, so that's a 95. So k is equal to 95. Here I'm saying m is adding a negative 17, so I need to subtract a negative 17, which is also the same as adding 17. So that's going to give me negative 14 is equal to m. Here I could do it two ways. I need to undo what's being done to the a. It's being multiplied by 2, we're subtracting 7, and then that whole quantity is being multiplied by 5. So this piece has to be dealt with first. I can either distribute it, or I can divide everything by 5. I'm going to distribute it, just because I feel like it. And when I distribute and multiply times both parts, now I've got negative 95 equals 10a minus 35. I need to undo this minus 35, so I'll do a plus 35. It's going to leave me with negative 60 equals 10a. I don't want 10 a's, I just want 1a. So I'm going to divide by 10, because that's the opposite of multiplying by 10, which is what we see now. And I see that a is equal to negative 6. All right. Again, kind of mixed up one. I got to do this. So I'm going to distribute first. Negative 7 plus 5m minus 15. A lot of people make mistakes with that. Equals 4m minus 27. Now I've got m's and constants on both sides. That's not what I want. So I'm going to move all of my constants over to the right. Instead of a negative 7 here, I'm going to add a positive 7 here and another positive 7 here. Instead of a negative 15 here, I'm going to add a positive 15 and a positive 15. Again, I always have to do the same thing to one side of the equation as I do to the other side of the equation. And that then gets me 5m is equal to 4m. This is 22, so that's going to be minus 5. And now I want my m's over here. This is, even though this is subtracting 5, the 4m is positive, so I'm going to do the opposite, negative 4m. And that leaves me with m is equal to negative 5. All right, more distributive property here. Negative 30 minus 54r equals 10 minus 50r. All right, so let's bring the constants over here. This is a negative 30, so we'll do a positive 30. This is a negative 50r, so we'll move that over here. So that's going to be a positive 50r. This goes away. This becomes negative 4r. This becomes 40. This goes away. I don't want negative 4r's. I want just 1. So we'll divide by the negative 4. And when I take those away, 40 divided by a negative 4. Well, 40 divided by 4 is 10. And a positive divided by negative is a negative. So my answer is negative 10. Okay, solving a system by elimination. Elimination is a process of making either the x or the y eliminate. In other words, cancel out. And you'll remember that I can add whatever I want to this equation as long as I add the same amount to the right as to the left. So what I'm going to do is I'm going to add 20 to the right. And I could add 6x plus 2y to the left, and those would be the same. Unfortunately, that's not exactly what I want, because I don't want my y's to become 6y or my x's to become negative 4. I want to make my y's go away. I see that I can turn a 2y into an opposite of this, negative 4y, by multiplying this whole expression by this whole equation by negative 2. Negative 12x minus 4y equals negative 40. Now, I'm going to take my original equation, and this manipulated equation, I'm just going to add them straight down. The reason I know I'm ready for this is because I've set it up that my 4y and my negative 4y are ready to cancel, be eliminated. So negative 26 and negative 40 is negative 66. 4y and negative 4y cancels, becomes 0. This becomes negative 22x. But I don't want a negative 22x, I want just 1. So negative 22 is my divisor, and I get x is equal to 3. I'm not quite done, because to solve this system, I should end up with a coordinate, an x value, which is going to be 3, and a y value that I haven't figured out yet. So I'm going to take this x value and plug it into this first equation. Negative 10 times 3 plus 4y is equal to negative 26. Negative 30 plus 4y is equal to negative 26. Add 30 to both sides. 4y is equal to 4, divided by 4. and I get y is equal to 1. In other words, I'm saying that when x is 3, y is 1 for this equation. And the whole point of this is I'm solving a system. I should have found, been doing the same process, this match. 3 and 1 also works in this one. Let's just try it. If I do 6 times 3 plus 2 times 1, that should equal 20. 6 times 3 is 18. 2 times 1 is 2. That does equal 20. In other words, I've just validated that, in fact, the point I found, 3, 1, is the only point that exists for both this and this equation. It's a point of intersection between those two lines if we were to graph them. So now we're solving by substitution. This is a second way of taking two linear equations, both in two variables, same two variables, and finding where they meet, the one point that exists for both of them, right? They're both like graphs, and there's one point where they both exist. So the easiest way to do this is to solve one of the equations for a single variable. This one has a 7, this one has a 6, this one has a 5. They've got leading coefficients that makes it confusing. But this x is all by itself. So I'm going to take this equation, I'm going to add 7y to both sides. It's going to leave me with x equals 7y minus 4. Now, I'm going to take this equation, and I'm going to rewrite it. But instead of the x, I'm going to put in a parentheses, placeholder, plus 5y equals negative 13. Now, instead of x, I'm going to plug in what x is equal to. In this case, I know that for this system, these two equations, that x is this. And for the one point in space I'm looking for, this x has this relationship. So I'm going to put in 7y minus 4. And I'm going to solve this now. Distribute the negative 6 through, negative 42y, negative times negative is a positive 24, plus 5y equals negative 13. I'll subtract the 24 from both sides, and I get negative 42y plus 5y equals negative 37. These are both on the same side of the equation, so I'm not going to do the opposite and say plus 42. Instead, I'm just going to combine like terms. That's going to give me a negative 37y is equal to negative 37 divided by negative 37. And I get y is equal to 1. And again, that's only half the solution. I know that I'm looking for a coordinate pair. I know that my y is 1. So I need to plug that back in and find out what my x is. It's better to not plug it into one you adapted. It's better to plug it into one of the originals. So I'm going to plug it into my original here. X minus 7 equals negative 4. Add 7, x equals 3. Wow, it's the same as that one. Okay. And let's just double check it. I'll plug it in here. Negative 6 times a 3 plus 5 times a 1 is supposed to equal negative 13. This is negative 18 plus 5 is supposed to equal negative 13. And it does. Negative 13 equals negative 13. Check. So this is my coordinate, 3, 1. All right, now we're doing geometric sequences and exponential. Well, a geometric sequence means that I'm looking for a growth between these two. In other words, a common ratio. So if I take my second term divided by my first term, and I take my third term divided by my second term, I should continually get this same ratio. So this is asking for the 3 terms in the sequence after the last one given. So in other words, this times 4 makes 12, this times 4 makes 48, this times 4 makes that. So I'm looking at doing this times 4. All right, so 192 times 4. Well, that one's kind of easy because it's really 200 times 4, so it'd be 800. But I'm 8 shy of this, so 4 times 8 is 32 shy of that. So the next number would be 768. And then if I multiply 768 by 4, that's a little bit harder, but let's do it the long way. 4 times 8 is 32, plus 3 is 24 is 27, carrier 2, 4 times that is 28, plus 2 is 30, comma 3072. And if I do that times 4, I'm going to have 8, and that's 28 carrier 2, it's going to be 2, and that's going to be 12. 12288. And just to double check, since I'm doing an answer key, I'm going to use a calculator on this. So 192 times 4 is equal to 768 times 4 is equal to 3072 times 4 is equal to 12288. Good. All right, now we're going to sketch the graph. Okay, so it doesn't have to be perfect. I know that in general, my exponential graphs look like this. But that would be something like a y equals 2 to the x. In this case, my base function is 1/2. That's the same as y is equal to 2 to the negative x, which is the same as, because 2 to the negative is the same as 1/2. So what's going to be happening here is it's going to have a reflection over the y-axis. In other words, instead of looking like this, it's going to look like this. It's still going to go through this point, but then it's got to flip, because this is a reflection over the x-axis. So now it's going to go down like this. But instead of being as steep as it was supposed to be, normally what we would expect is this point should be at 0, 1, and then here it would be at 1, 2, and then 2, 4. Here would be -1, 1/2. So to flip it, we're expecting that this would be at 1, 1/2, 0, 1, and then -1, 2. So when we flip it over, this is going to be 1, -1/2. This is going to be -1, -2, but we're multiplying all these by 1/3. So we're still going through this point, but now since it's got a 1/3 factor, this is going to be down here at 1/3. And this is going to then be at 1, it's going to be 1/2 times 1/3 is going to be -1/6. But when I'm over here at -1, 1/2 to the -1 is 2. So this is going to be at -2/3. And when I have a 2 there, I'm going to have a -2. I'm going to have 4 times this. Now I'm over that 1 point. It's going to end up looking something like that. All right, radical expressions. So to simplify this, what I need to do is factor this. I know that 72 is 36 times 2, which is 6 times 6 times 2. So I'm going to express this as 6 times 6 times 2 times p times p times p times p. And when I'm doing a radical simplification, what I'm looking to do is find things that show up twice. And each of those will come out as a single thing. So 6 p times p is p squared, and then there's still a 2 stuck on the inside. All right, so now we're going to look at what this factors into. 576, well, it's an even number, so I know 2 goes into that. 576 divided by 2 is 288. And that's 2 and 144, and I know 144 is 12 and 12. So I'm going to treat this as 6 times 2 times 2 times 12 times 12 times n times n times n. That's my factorization of this. The 2's show up. So I still had the 6 on the outside. Now there's a 2 on the outside. It's 12 there. So now there's a 12 on the outside. There's an n there, and then there's one n, and that's the only thing stuck on the inside. 6 times 2 is 12 times 12 is 144. So this comes out to 144 n root n. All right. Simplify. Same idea here. I'm just going to take this and say the 3 is already on the outside. The 12 is 2 times 2 times 3. There's only one x. There's 3 y's. And there's 5 z's. So the 2's come out. 3 times 2. There's a y that can come out. And there's 2 z's. So z squared. And what's stuck on the inside is what's left here. 3x, y, z. And this would come out to 6yz squared root 3xyz. All right, now we're simplifying exponents. Anything that's got a base of x and is multiplied, I can add the exponents. So I'm going to have x with a -2 plus a 4 plus a -2, and then times y, which is going to have an exponent of 4 plus 3. And then there's this 2 in there. And this 4 is not actually an exponent over 2. 2 is being multiplied by it. So it's really just times a 2 to the first. Well, -2 plus 4 minus 2, this is x to the 0th. And this is y to the 4 plus 7, so y to the 7th. And this is times 2 to the first. Anything to the 0th is just 1. Normally we put our constants in front of our exponents. So this solution would be best written as 2y to the 7th. If I have a 3 here, I can't distribute this through everything. It is multiplication, not addition. So I can distribute it across the exponents. In other words, I can say that it's negative 1 y squared, and this is to the first, times negative 2 to the first, x to the first, y to the negative fourth, and this is all to the third power. I'm going to do first what we did here. If this is y to the second, and this is y to the negative fourth, I'm going to combine those two together. So we've got a negative 1 times negative 2. I'm just going to group those together. And this is y to the negative 2. And now, if I distribute this exponent, this becomes negative 1 cubed. Negative 1 times negative 1 times negative 1 remains negative 1. Negative 2 cubed is negative 2, 2, 2. So it's negative 8, x to the third, y to the negative 6, multiplying each exponent by 3. Negative 1 times negative 8 is a positive 8. And so I get 8 cubed, y to the minus 6. This does say containing only positive exponents. So I'm going to have to take this negative 6 and put it somewhere else, because a negative exponent means it jumps to the other side of the fraction bar. So in other words, a negative 6 on top becomes a y to the positive 6 on the bottom. There's my solution. All right, sketch each linear equation. Boy, this is not in great format. The numbers happen to work out, though. I can either take y equals mx plus b and graph it and say my y-intercept is negative 4 because that's the constant. And then my slope is a rise, 1, 2, 3, over a run of 2 because it's 3 over 2. My slope is 3 over 2. And my b, my y-intercept, is equal to negative 4. So I start with that, and then I go up 1, 2, 3, 4. Nope, sorry, 1, 2, 3 over 2. And if I were to just connect these, I produce a line that matches that. And any point along this line that I plug in 4, 2, for example, if I put in 4 here, 3 times 4 is 12, over 2 is 6, 6 minus 4 is 2. In other words, that's the matching y value. All these points satisfy this equation. I could do the same thing here, and if I wanted to, I could just move the 4x and call this y is equal to negative 4x plus 4, say that my b is equal to 4, and my slope is equal to negative 4 over 1, because this could be over 1. And I could graph it the same way. But I could also graph this looking for x and y intercepts. If I have 2 points, I can connect them to make a line. Well, my x-intercept happens when y equals 0. So if y is equal to 0, that means 4x equals 4, so x is equal to 1. In other words, x is 1 when y is 0. And if I did it the other way and said, okay, what if x were 0? Then I see that y is equal to 4. If x is 0, y is equal to 4. So these two coordinates I can connect. It's a really bad drawing. And that would be my graph of 4x plus y equals 4. Notice I've got arrows on the end to show that it goes on forever. Okay, find the slope through each point. Well, our slope equation is y equals y2, x equals m equals y2 minus y1 over x2 minus x1. In this case, this is an x and this is a y. This is an x and this is a y. I'll call this my first point and this my second point. So I'm going to take the difference in the y's. So I'm going to say 5 minus negative 15 over negative 3 minus 3. Minusing a negative is the same as adding. So that's 20 and negative 3 minus 3. Those are both in the same direction. So over negative 6, I can reduce this to call this negative 10/3. That's my slope. Write the slope-intercept form of this equation. Okay, slope-intercept form. That's y equals mx plus b, because this is my slope. This is my intercept. All right, I've already got my slope, and I know a point. So I know it's going to be y equals 1x, because my slope is 1, plus some y-intercept. I don't know what that is. But if I take this as my y value, and this as my x value, I can find the value of b that makes this equation work. 2 equals 1 times negative 1 plus b. That means 2 is equal to negative 1 plus b. I want to get rid of a negative 1, so I'm going to add 1. I'm going to get 3 is equal to b. Therefore, my equation is y is equal to not m, because I know it's 1, x plus my b is equal to 3. Right, the slope-intercept form of this equation. Okay, slope-intercept. So I need my slope, and I need my intercept. Looks like this is 1, 2, 3, 4, 5. Like my intercept is at the point 0, 5. So I know my equation is going to be y equals something x plus this 5. Now I need my slope. So I need to go from this point down to another point that seems to be on, that's not that clear. This one down here, I think, is a better one. I need to find what are called lattice points, so that as I go 1, 2, 3, 4, 5, 6, 7, 8 over 1, 2, 3, it's perfectly hitting a crossing point. So it goes up 8 over 3, so this would be an 8/3, rise over run. All right, quadratic expressions, find each product. This is foiling. So I'm going to do 4x times 5x is 20x squared minus 12x. Inner terms minus 10x plus 6, and I'll combine like terms and I'll get 20x squared minus 22x plus 6. That's it. 29 is similar multiplying. Ooh, this one's a difference of 2 squares, though. Notice how they're the same. 7v minus 8, 7v plus 8. This is going to be special. It's going to give me 49v squared plus 56v minus 56v. The reason this is special is because those two will cancel, minus 64. And so since these two cancel out, I end up with what's called a difference of 2 squares. This is a perfect square. This is a perfect square. All right, to factor this one, I'm going to be looking for 2 numbers that multiply to make 80 and at the same time add to make 18. Well, those are 10 and 8. So I'm going to split this up strategically. A squared plus 10a plus 8a plus 80. In other words, instead of 18a, I broke it up into 10a and 8a because of this. Then I'm going to look at these two and say, what's common to both of those? Well, it's a. So I factor that out of each and I get a plus 10. And then I say, what's common to these? And I factor out the 8. And I also get 8 plus 10. And if I did this correctly, I expect these inner terms to match. Now I'm going to look anew at this and I say, what's common to this term and this term? And it's a plus 10. So I factor that out. What I'm left with is a plus 8. And that's the factorization of this. Solving this completely by factoring means I'm going to factor it the same way I did here and then solve it. So first I'll do the x. It's got to multiply to 4 and add to a -5. And so I'm going to put a -4 and a -1 in here. And that means it's going to be x squared minus 4x minus 1x plus 4 equals 0. What's common to these two is an x minus 4. What's common to this is a -1 x minus 4 equals 0. This is the common part now, so I'll pull that out and get x minus 4 and x minus 1 equals 0. And now I'm going to apply something called the zero product property. If these two expressions multiply together to make 0, then either x minus 4 equals 0, so x equals 4, or x minus 1 equals 0, so x equals 1. Those are the two values that would make this equation work. If I plug in 1 minus 5 plus 4 makes 0. If I plug in 4, 16 minus 20 plus 4 equals 0. All right, that's the homework for today. I hope that makes sense to you.